Well, happy Tuesday to everybody as we kick off another week. I hope you enjoyed a really nice long weekend. So beautiful, so beautiful. So I hope you got outside and just soaked up that glorious Southern California sunshine. We might get a little rain this week, so we'll see how that goes. But chapter 8, so we're going to circle back and spend this chapter talking about sequences and integrals that are improper. So we're going to kick that off in 8.1 with talking about sequences. There are a couple different kinds of sequences. We have explicit and recursively defined sequences, and sequences that follow both arithmetic and geometric patterns. And we'll talk about their limits and the words convergent and divergent and how those apply. We'll be using those a lot throughout the coming chapters, and so we're going to get real conversant in what convergent and divergent mean. A sequence is always indicated with these brackets, so you'll get good at drawing brackets, and when we have a bracket, that means we're talking about a sequence. A sequence is a list of numbers, often written in comma form, separated, and some sequences are finite, which means they come to an end, and many sequences are infinite, which means they would continue on. We use subscripts to distinguish the different terms. So a sub 1, a sub 2, a sub 3, etc. A sub n being an indeterminate term, a position in the sequence. So sequences can be defined in what we call explicit or recursive ways. An explicit sequence is determined by its connection to the positive integers. So it is determined by a formula, we'll say, based on n being 1, 2, 3, 4, etc. So it's always a formula with an n in it, and n represents the set of positive integers starting with the number 1, and you generate the sequence by plugging in the number 1 and getting the first term, and plugging in the number 2 and getting the second term, etc., etc. So that's what explicit means. It means you can jump around in a sequence. If you know the n value, then you can find the nth term of any sequence. So a recursive sequence is determined by a different kind of formula. And the formula is not based on a sequence of numbers where you go 1, 2, 3, 4. It's determined by a formula based on the value of the previous term. So you have to have an initial term to get you started. Once you have an initial term value, then you'll have a formula to follow, which will tell you what to do to that term value. So if you have an initial value and you're told to square it and subtract 5, that will give you another value. And then you square that one and subtract 5. And then you square that one and you subtract 5. That's recursive, where it's always based on the value of the preceding term. It's not based on 1, 2, 3, 4, where you're plugging in numbers in a specific numerical order where you don't skip any integers. Your values are going to jump around. They could switch from positive to negative very easily, and it's always based on the next term being generated by the previous term. So let's look at these two. Here's an explicit sequence. I can tell it's explicit because the equation has an n clearly defined in it. So if we want the first 4 terms, then we are going to have to plug in 1, 2, 3, and 4. All right, so the first 4 terms, A1, A2, A3, and A4. If I plug in the number 1 into this equation in both positions for n, I'll have a numerator value of -1. I'll have a denominator value of 3. If I plug in the number 2, I will have a numerator value of 1. I will have a denominator value of 6. If I plug in number 3, I will have a numerator value of -1. I'll have a denominator value of 11. If I plug in the number 4, +1 would be my numerator, and let's see, 18 would be my denominator. So that is my sequence of the first 4 terms. If I want to find the 100th term, I simply drop the number 100 into both the numerator and the denominator. That will give me 1 for my numerator, and then I'll have 100 squared plus 2. So 100 squared is 10,000 plus 2, so I'll have 1 over 10,002 is the 100th term of the sequence. So that's an explicit formula. Here's a recursive one. Find the first 3 terms and the 7th term for the sequence if you have the following conditions. B1 is 4, and all of the rest of them take the previous term. So Bn is based on Bn minus 1, B sub n minus 1, subtract 2. So I'm looking for B1, B2, and B3. B1 is given to be 4. After that, I take the value of the previous term and I subtract 2. And then I take the value of that term and I subtract 2. So the first 3 terms are 4, 2, 0. Well, what about the 7th term? So the downside of a recursive sequence is I can't just jump to the 7th term. In order to get to the 7th term, I have to know the 6th and the 5th and the 4th and the 3rd, 2nd, and 1st. I have to know all the terms preceding that. And so I'm going to have to continue subtracting 2. So I've got my 1st term, 2nd term, 3rd term, 4th term, 5th term, 6th term, and my 7th term. So B7 sub 7 is a value of -8. And so you have to generate a recursive sequence in order. It's very difficult to jump ahead. So imagine if I'd had to do the 100th, I would have maybe had to figure out a different way to do that rather than getting them all in order. So that's how sequences are defined. There are different types of sequences already based on the pattern that is formed. An arithmetic sequence, now it looks like the word arithmetic, which is one way you can pronounce it, but in this context it's pronounced arithmetic. So think like a paramedic, it's pronounced the same way, arithmetic. An arithmetic sequence is based on addition, and the addition is based on the constant of d. So the first time, starting with the value of a, I add 1d, and then I add 2d, and then I add 3d, and then I'm going to add successive values of the common difference. So arithmetic sequences follow a pattern of addition. Now that is not to say that subtraction is not arithmetic. Subtraction is also arithmetic because subtraction is simply adding a negative number. That's the definition of subtraction. And so subtraction would also fall under the category of an arithmetic sequence. This format right here, a plus n minus 1 times d. More specifically or more commonly, you would see a sub 1 written there, okay? And so you would say an arithmetic sequence, a sub n, is defined as a sub 1 plus n minus 1 times the common difference of d. And that formula will generate an arithmetic sequence. If you know the first term and you know the difference maker, then you can come up with the arithmetic sequence. So given the following arithmetic sequence, let's just verify that it's arithmetic. This is a +4 and +4. All right, so yep, I can confirm that the common difference is +4. All right, so how would I find the 9th term? Well, I could just do it in order by continuing to just add 4 every time, continuing from where I was. So I could say, okay, well, I was at 9, and then it would be 13, and then 17, and then 21, and then 25, and then 29. Which one of those have I gotten to the 9th term yet? So this is 4th, 5th, 6th, 7th, 8th, and yep, I got to the 9th term. So that would be one way to do it, is to just figure them out in order. But it's often more helpful in Part C to have an explicit rule for that nth term. So how would I write an explicit rule for this? Well, a sub n is the value of a sub 1 plus the quantity n minus 1 times the difference maker. So in this case, the first term was -3, the quantity n plus minus 1, and then times the difference maker of 4. And so if I wanted to find the nth term directly, or explicitly, the 9th term, then I would say, okay, well, the 9th term would be -3 plus 9 minus 1 times the common difference of 4. So that's -3 times 8 times 4, -3 plus 32, 29. Sure enough, that's what I got when I found it, sort of by brute force. A geometric sequence is written in the form of is based on the pattern of multiplication. We are multiplying by r, and then by r again, and then by r again, and this is multiplying what we call the common ratio r, as long as r is not 0. Okay, so make sure it's not a 0 value. Okay, then that would not make any sense. If we just kept multiplying by 0, that'd be a very boring sequence. So again, we can define its geometric patterns are based on multiplication, but not just multiplication. Okay, also division. Because remember, the definition, just as subtraction is defined as adding a negative, division is defined as multiplying by the reciprocal. And so if you just train your mind to not think of it as division, but to think of it as multiplying by a reciprocal, then you have identified a geometric pattern. So the formula for that is that all geometric patterns start with the first term multiplied by r to the quantity power of n minus 1. And that would generate a geometric sequence. So here is an example of a geometric sequence. I can look at that and I can tell that the multiplier each time is multiplying, or I'll use, what do I multiply to move from one term to the next? And the multiplier is -3. Okay, now I want to go to the 10th term, so I can either continue to multiply by -3, multiply by -3, multiply by -3, or I can write an explicit rule, which is what I'm going to do. So a sub n is a sub 1 times the multiplier to the quantity n minus 1. So for this problem, it would be 1 is the first term, and then the r is -3 to the n minus 1 power. So if I want the 10th term explicitly, then I plug 10 in. So 1 times -3 to the 10 minus 1. So I'm looking at -3 to the 9th power. And there's really, you don't need to give me an exact answer. You can leave it in its power form. It's fine. All right, so can you work backwards from that? What if you know it's geometric, but you don't have all the terms in a row? So this one, I had the first 4 terms, and they were given to me in order, the first 4 terms right in a row. But what if I don't have that? What if I've got the 2nd and the 5th? Or what if there's a bigger gap even between those? Would it be possible to figure out what those, what the common ratio is? And the answer is yes, there is. Okay, so what if we know that the second term, so a sub 2, is the first term times an r to the 2 minus 1 power. Okay, and we know that that is supposed to be -6. So -6 equals a sub 1 times r to the first. And what if we also know that the fifth term, a sub 5, would also be a sub 1 times r to the 5 minus 1. So that would be 48 equals a sub 1 times r to the fourth. Is it possible to solve that simultaneously so that we could figure out what the r value is? Okay, and yes, if we get a sub 1 here alone, a sub 1 is -6 divided by r. And so I can substitute that into the other equation. -6 over r times r to the fourth. So 48 is -6r cubed. So r cubed is 48 divided by -6, which is -8. So r must be -2. So I can figure out my common ratio using just some basic algebra. From that, I can work backwards, and I now know the multiplier, and I know the explicit term. So let's kind of fill in the gaps here. We have blank, and then -6, and then blank, and then blank, and then 48. So we know our multiplier is -2, which means this term has to be 12, and that has to be -24. So if the multiplier is -2, that means the first term had to be 3. So now I can write my explicit formula that all values for this geometric term are a sub 1 times r to the quantity n minus 1. So all terms could be generated by 3 times -2 to the n minus 1 quantity. And that would be my explicit rule for that geometric sequence. So can I find an explicit rule for the following? So I just need to determine what's going on between each term. So moving from one term to the next, I would need to define what the common pattern was. So here I can see that the pattern, is based on a multiplier. R is multiplied by -2. So then my explicit rule would be all a sub n's are generated by -2 is the first term, -2 is also the multiplier, and n minus 1. All right, the next one. How do I move from term to term? Now some people get a little bit duped, and they think, oh, this is a multiplier again, and they think that multiplier is 3 because they look at the 2 and the 6 and the 18 and the 54, and they think, oh, that looks like multiplying by 3. Okay, but it's not a multiplication pattern. Natural logs don't work that way. What you need to do is you need to see this as an addition problem. So let me help you understand. This is the natural log of 2. It's the natural log of 2 times 3. That's how we get 6. It's the natural log of 2 times 3 times 3 again. That's how we get 18. It's the natural log of, I'll put some parentheses here, 2 times 3 times 3 times 3. So yes, definitely multiplying by 3 has something to do with it, but it's within the parentheses. So let's remember what that means about natural logs. That's the natural log of 2, and then multiplication is the natural log of 2 plus the natural log of 3. And the next one would be the natural log of 2 plus the natural log of 3 plus another natural log of 3. And then the last one would be the natural log of 2 plus the natural log of 3 plus that natural log of 3 plus another natural log of 3. So this is not a multiplication pattern at all. This pattern is addition. This pattern is D equals ln 3. ln 3 is not being multiplied, it's being added every time. That's the consistent pattern. So this is an arithmetic pattern. And the arithmetic pattern says you take your first term and then plus the quantity n minus 1 times the multiplier value. And so that is the expression, the natural log of 2 plus the quantity n minus 1 times the natural log of 3. So be careful that you're not reading into it what you want it to be, but what's actually there. Graphing. Right, when you create a graph on your calculator and you want to do a sequence, please make sure you are in parametric mode. You also have to distinguish between connected and dot. Under the mode options, you'll see that there is something called connected, which is what we usually use, and something called dot. You want to make sure that you have picked the dot option. If you leave it on connected, then your graph would look like this. And all the dots would be connected to each other. And that would mean that the domain was all those integer values in between. Okay, but a sequence is not all the integer values. The domain is not all real numbers. The domain of sequences are the positive integers. And what's generated from that are distinct points, distinct dots. And so make sure you are in dot mode, and that what is generated then are only the dots that are associated with the positive integers. Okay. All right, let's talk about convergence and divergence. This has to do with when you take a limit of your sequence. So we want to take the limit as n approaches infinity and see what happens. If you take the limit of the sequence as n approaches infinity and you get L, L is a constant. If you get a constant value after you take the limit of the sequence formula, we call that convergent. Okay, it will converge if you approach a constant. If you do not have a limit, if the limit does not exist, we say the limit diverges or is divergent. So if you're asked about convergence or divergence, take the limit of the explicit formula and see what happens. All right, so here is a sequence generated by the term 2n minus 1, or by the expression 2n minus 1 over n. And we want to determine if the sequence converges or diverges. So I'm going to take the limit as n approaches infinity of the sequence a sub n. And so then I want to take the limit of the explicit formula, 2n minus 1 over n. I want to simplify that. Remember, one of the rules is when you're approaching infinity, you want to divide everything through by the highest power of the variable expressed. So I'm going to divide everything through by n. And so I'm going to end up with 2 minus 1 over n. All right, then I'm going to substitute in infinity. So I get 2 minus 1 over infinity. We know that 1 divided by infinity is 0, and 2 minus 0 is 2, which is a constant. And so this is a convergent sequence. What that means is that the terms will converge to the number 2. They may not ever actually get there, but they will converge towards the number 2. So the farther out towards infinity we get, what's generated, the result, will start to just look around, basically more or less, to 2 every single time. So this is a convergent sequence. We apply the same limit technique to this explicit sequence, -1 to the n times n minus 1 over n. So we'll do the same thing. This is a product this time. And so the limit of the sequence is the product of the limits. So I have the limit of n minus 1 to the n, but I also have a separate product, and n minus 1 over n. All right, there's not a whole lot I can do with -1 to the n, but I can simplify this term to 1 minus 1 over n. Oops, I think I made a mistake here. That should be a multiplication. Okay, so now I've got this being 1 minus 1 over infinity, or 0. And so I've 1 minus 0, so I've really just eliminated this whole term multiplying by 1. All right, well, does what I have left approach a constant? This should say infinity. Okay, good. All right, well, let's think about what's actually generated here, starting with the number 1. So if I plug the number 1 into this sequence, I get -1. If I plug 2 in, I get +1. 3, -1, +1, -1, +1, etc. This does not converge to a single constant. This is what's called alternating. This alternates between 2 values. It's either 1 or -1, 1 or -1, and it will be that way for infinity. It will never converge to a single constant value. Now, I know each of them are constant, like -1 is a constant and 1 is a constant, but they're not the same constant. And so this is not a convergent sequence. This is a divergent infinite sequence because it fails to converge to a single constant value. Okay, so it had to be a single constant value. So this is called alternating, very famous. An alternating sequence is always going to be divergent. Okay, when those values flip-flop back and forth and never approach a single value. All right, so that's your intro to sequences, both explicit and recursively defined sequences, and sequences that follow patterns of arithmetic or geometric formulas, and then you'll be looking for convergent versus divergent. So you've got all these dichotomies, right? So you've got explicit or recursive, you have arithmetic or geometric, you have convergent or divergent. So these are two polarizing ideas, two polar opposites, all wrapped up in the same topic of sequences. All right, we'll get back together on Wednesday. We'll talk about this, and we'll move forward into seeing how these help us with defining improper integrals. All right, I hope you have a good start to your week, and I look forward to Wednesday.